Large language model. A large language model, LLM, is a language model consisting of a neural network with many parameters, typically billions of weights or more, trained on large quantities of unlabeled text using self-supervised learning. LLMs emerged around 2018 and perform well at a wide variety of tasks. This has shifted the focus of natural language processing research away from the previous paradigm of training specialized supervised models for specific tasks. Though the term large language model has no formal definition, it often refers to deep learning models having a parameter count on the order of billions or more. LLMs are general-purpose models which excel at a wide range of tasks, as opposed to being trained for one specific task, such as sentiment analysis, named entity recognition, or mathematical reasoning. The skill with which they accomplish tasks, and the range of tasks at which they are capable, seems to be a function of the amount of resources, data, parameter size, computing power devoted to them, in a way that is not dependent on additional breakthroughs in design. Though trained on simple tasks along the lines of predicting the next word in a sentence, neural language models with sufficient training and parameter counts are found to capture much of the syntax and semantics of human language. In addition, large language models demonstrate considerable general knowledge about the world, and are able to memorize a great quantity of facts during training. LLMs have been observed to confidently assert claims of fact which do not seem to be justified by their training data, a phenomenon which has been termed hallucination. While it is generally the case that performance of large models on various tasks can be extrapolated based on the performance of similar smaller models, sometimes large models undergo a discontinuous phase shift, where the model suddenly acquires substantial abilities not seen in smaller models. These are known as emergent abilities, and have been the subject of substantial study. Researchers note that such abilities cannot be predicted simply by extrapolating the performance of smaller models. These abilities are discovered rather than programmed in or designed, in some cases only after the LLM has been publicly deployed. Hundreds of emergent abilities have been described. Examples include multi-step arithmetic, taking college-level exams, identifying the intended meaning of a word, chain of thought prompting, decoding the International Phonetic Alphabet, unscrambling a word's letters, identifying offensive content in paragraphs of English, a combination of Hindi and English, and generating a similar English equivalent of Kiswahili proverbs. Large language models have most commonly used the transformer architecture, which, since 2018, has become the standard deep learning technique for sequential data. Previously, recurrent architectures such as the LSTM were most common. LLMs are trained in an unsupervised manner on unannotated text. A left-to-right transformer is trained to maximize the probability assigned to the next word in the training data, given the previous context. Alternatively, an LLM may use a bidirectional transformer, as in the example of BERT, which assigns a probability distribution over words given access to both preceding and following context. In addition to the task of predicting the next word or filling in the blanks, LLMs may be trained on auxiliary tasks which test their understanding of the data distribution, such as next sentence prediction, NSP, in which pairs of sentences are presented and the model must predict whether they appear side by side in the training corpus. The earliest LLMs were trained on corpora having on the order of billions of words. The first model in OpenAI's GPT series was trained in 2018 on book corpus, consisting of 985 million words. In the same year, BERT was trained on a combination of book corpus and English Wikipedia, totaling 3.3 billion words. Since then, training corpora for LLMs have increased by orders of magnitude, reaching up to hundreds of billions or trillions of tokens. LLMs are computationally expensive to train. A 2020 study estimated the cost of training a 1.5 billion parameter model, 2 orders of magnitude smaller than the state-of-the-art at the time, at $1.6 million. Advances in software and hardware have brought the cost substantially down, with a 2023 paper reporting a cost in the hundreds of thousands of dollars to train a 12 billion parameter model. A 2020 analysis found that neural language models' capability, as measured by training loss, increased smoothly in a power-law relationship with number of parameters, quantity of training data, and computation used for training. These relationships were tested over a wide range of values, up to 7 orders of magnitude, and no attenuation of the relationship was observed at the highest end of the range, including for network sizes up to trillions of parameters. Between 2018 and 2020, the standard method for harnessing an LLM for a specific natural language processing (NLP) task was to fine-tune the model with additional task-specific training. It has subsequently been found that more powerful LLMs such as GPT-3 can solve tasks without additional training via prompting techniques, in which the problem to be solved is presented to the model as a text prompt, possibly with some textual examples of similar problems and their solutions. Fine-tuning is the practice of modifying an existing pre-trained language model by training it, in a supervised fashion, on a specific task, e.g. sentiment analysis, named entity recognition, or part-of-speech tagging. It is a form of transfer learning. It generally involves the introduction of a new set of weights connecting the final layer of the language model to the output of the downstream task. The original weights of the language model may be frozen, such that only the new layer of weights connecting them to the output are learned during training. Alternatively, the original weights may receive small updates, possibly with earlier layers frozen. In the prompting paradigm, popularized by GPT-3, the problem to be solved is formulated via a text prompt, which the model must solve by providing a completion, via inference. In few-shot prompting, the prompt includes a small number of examples of similar problem, solution, pairs. For example, a sentiment analysis task of labeling the sentiment of a movie review could be prompted as follows. Review, this movie stinks. Sentiment, negative. Review, this movie is fantastic. Sentiment. If the model outputs positive, then it has correctly solved the task. In zero-shot prompting, no solve examples are provided. An example of a zero-shot prompt for the same sentiment analysis task would be the sentiment associated with the movie review, this movie is fantastic. Is. Few-shot performance of LLMs has been shown to achieve competitive results on NLP tasks, sometimes surpassing prior state-of-the-art fine-tuning approaches. Examples of such NLP tasks are translation, question answering, close tasks, unscrambling words, and using a novel word in a sentence. The creation and optimization of such prompts is called prompt engineering. Instruction tuning is a form of fine-tuning designed to facilitate more natural and accurate zero-shot prompting interactions. Given a text input, a pre-trained language model will generate a completion which matches the distribution of text on which it was trained. A naive language model given the prompt, write an essay about the main themes of Hamlet, might provide a completion such as, a late penalty of 10% per day will be applied to submissions received after March 17. In instruction tuning, the language model is trained on many examples of tasks formulated as natural language instructions, along with appropriate responses. Various techniques for instruction tuning have been applied in practice. OpenAI's InstructGPT protocol involves supervised fine-tuning on a dataset of human-generated, prompt, response, pairs, followed by reinforcement learning from human feedback, RLHF, in which a reward function was learned based on a dataset of human preferences. Another technique, self-instruct, fine-tunes the language model on a training set of examples which are themselves generated by an LLM, bootstrapped from a small initial set of human-generated examples. The most basic intrinsic measure of a language model's performance is its perplexity on a given text corpus. Perplexity, which is closely related to the cross-entropy loss function used to train neural language models, is a measure of how well a model is able to predict the contents of a dataset. The higher the likelihood the model assigns to the dataset, the lower the perplexity. Because language models may overfit to their training data, models are usually evaluated by their perplexity on a test set of unseen data. This presents particular challenges for the evaluation of large language models. As they are trained on increasingly large corpora of text largely scraped from the web, it becomes increasingly likely that models' training data inadvertently includes portions of any given test set. A large number of testing datasets and benchmarks have also been developed to evaluate the capabilities of language models on more specific downstream tasks. Tests may be designed to evaluate a variety of capabilities, including general knowledge, common sense reasoning, and mathematical problem solving. One broad category of evaluation dataset is question-answering datasets, consisting of pairs of questions and correct answers. For example, have the San Jose Sharks won the Stanley Cup? No. A question-answering task is considered open book if the model's prompt includes text from which the expected answer can be derived. For example, the previous question could be adjoined with some text which includes the sentence, "The Sharks have advanced to the Stanley Cup Finals once, losing to the Pittsburgh Penguins in 2016. Otherwise, the task is considered closed book, and the model must draw on knowledge retained during training. Some examples of commonly used question-answering datasets include Truthful QA, Web Questions, Trivia QA, and Squad. Evaluation datasets may also take the form of text completion, having the model select the most likely word or sentence to complete a prompt. For example, Alice was friends with Bob. Alice went to visit her friend, ______. Some composite benchmarks have also been developed which combine a diversity of different evaluation datasets and tasks. Examples include GLUE, Superglue, MMLU, Big Bench, and Helm. It was previously standard to report results on a held-out portion of an evaluation dataset after doing supervised fine-tuning on the remainder. It is now more common to evaluate a pre-trained model directly through prompting techniques, though researchers vary in the details of how they formulate prompts for particular tasks, particularly with respect to how many examples of solved tasks are adjoined to the prompt, i.e. the value of n in n-shot prompting. Because of the rapid pace of improvement of large language models, evaluation benchmarks have suffered from short lifespans, with state-of-the-art models quickly saturating existing benchmarks, exceeding the performance of human annotators, leading to efforts to replace or augment the benchmark with more challenging tasks. Some datasets have been constructed adversarially, focusing on particular problems on which extant language models seem to have unusually poor performance compared to humans. One example is the Truthful QA dataset, a question-answering dataset consisting of 817 questions which language models are susceptible to answering incorrectly by mimicking falsehoods to which they were repeatedly exposed during training. For example, an LLM may answer no to the question, "Can you teach an old dog new tricks?" Because of its exposure to the English idiom "you can't teach an old dog new tricks," even though this is not literally true. Another example of an adversarial evaluation dataset is SWAG and its successor, HelloSwag, collections of problems in which one of multiple options must be selected to complete a text passage. The incorrect completions were generated by sampling from a language model and filtering with a set of classifiers. The resulting problems are trivial for humans, but at the time the datasets were created, state-of-the-art language models had poor accuracy on them. For example, we see a fitness center sign. We then see a man talking to the camera and sitting and laying on an exercise ball. The man A. demonstrates how to increase efficient exercise work by running up and down balls. B. moves all his arms and legs and builds up a lot of muscle. C. then plays the ball and we see a graphics and hedge trimming demonstration. D. performs sits UPS while on the ball and talking. BERT selects B as the most likely completion, though the correct answer is D.